In this video, we are going to do problem number 32.02, GCD. All right, so I have it downloaded and opened up in Racket. So let's just go down here. This is going to be a generative recursion problem, so I recommend you try to answer these questions while you do the problem. All right, so problem A, design the function gcd-euclid that consumes two numbers and finds the greatest common divisor of the two. All numbers are divisible by 1, but they may or may not have more shared factors, right? So for example, given 6 and 25, notice that 6 is even and 25 is odd. So it's likely that they're not going to share many common factors. So 6 is evenly divisible by 1, 2, 3, and 6. 3 times 2 is 6, 2 times 3 is 6, and 6 times 1 is 6. All right, all numbers have a factor of 1. 25 is evenly divisible by 1, 5, and 25. 5 times 5 is 25, and 1 times 25 is 25. All right, they only share, and yet their greatest common divisor is 1. Because that's the only factor that they share. In contrast, 18 and 24 have many more divisors, many more common divisors, and their greatest common divisor is 6. So 18 is evenly divisible by 1, 2, 3, 6, 9, and 18. 18 times 1 is 18, 3 times 6 is 18, 9 times 2 is 18, 2 times 9 is 18, etc. 24 is evenly divisible by 1, 2, 3, 4, 6, 8, 12, and 24. Right? But their greatest common divisor is 6. All right, they both divide evenly. 18 and 24 both evenly divide into 6. Do this using the Euclidean algorithm. So we actually give you an algorithm, and it's your job to transcribe this into code form. So given two numbers n and m, let's call s the smaller of n and m, and l the bigger number. So if the smaller number is equal to 0, then the GCD is just l, since 0 divides anything even. All right. Otherwise, the GCD is GCD s and then L %s, which is percent means the modulo, so remainder. And here's a Khan Academy link for some more in-depth elaborated examples. So right over here, right? So if we find the GCD of 270 and 192, right, then we get, it's essentially going to be this, right? It's going to be 192 and then 78, because this second number over here, it's going to be the modulo. So let me just do that for you guys. Let me grab out my calculator. All right, so if you type in, so usually modulo is percent on your calculator, but in this case it's mod and this one. So 270 divided by 192 is going to get us 78, and that's why it's this. All right, and you can plug in these numbers and verify it. All right, so try to transcribe this algorithm into code form right over here. All right, there is the signature, purpose, stub. It's your job to write some examples and etc. All right, problem B is the structural recursion way of doing it. And you can get some ideas here, but this just demonstrates the structural recursion nature. We're going to benchmark it. So yeah, nonetheless, right, try to write the Euclidean algorithm based on this. All right, more spoilers in 3, 2, and 1. All right, I'm assuming that you guys took a good swing at it, so now let's go over it together. So let's just write some tests for these. Check, expect, gcd-euclid. So let's say 18 and 24. That's the one that they gave us up there. The greatest common factor between them is 6. All right, we can do a few more. We can do something like 6 and 4. All right, the shared factor is 2. Greatest common shared factor is 2. And we can do one last one. All right. So we can do something like 36 and 81. And the greatest common shared factor is 9, right? Because 9 times 4 is 36, and 9 times 9, well, not 9 times 9, but is 9 times 9 81? I think it is. Okay, there we go. GCD and an M, and then, okay, that's the stub. We can just run against the stub here. And we get a bunch of mismatches. GCD-Euclid, this function is not defined. Okay, I spelled it wrong. All right, that's why I run the test against the examples, stub against examples. And you just get differs. All right, that's cool. All right, so pause video and try to do this on your own. It's kind of difficult to template it. Again, you can use the generative recursion template right over here. It's going to look something approximately like this. In this case, we're not dealing with lists. We're dealing with just numbers, right? These are just numbers. So you're going to treat some of these as recursive types over numbers, right? But anywho, try to transcribe this algorithm in code form. I'll go for spoilers in 3, 2, and 1. All right, I'm assuming that you guys took a good swing at it. So now let's go over together. Don't fret if you don't get this, right? This requires some domain knowledge on math and really to get used to transcribing English into code. All right, so a description of an algorithm into code. All right, so let me just do that. So define gcd-euclid. Euclid. All right, so it takes in two numbers, n and m, and it says that let's call s the smaller of n and m and l the bigger. So that tells us immediately right away that we're going to need a local because we need to keep track of which one is smaller and which one is bigger. All right, so local, and then there we go. We can put dot dot dots there while we work this out. All right, so define s. So s, let's call s the smaller of n and m. All right, so given n and m, we need to determine which one of these two numbers are smaller, and we can do that. If you look in the documentation of Racket, then you would find that operations on numbers. I recommend that you actually stare at the documentation to get ideas actually, rather than staring at the code here. But here we go. It's going to be min. All right. That's how you get the minimum number between n and m. All right. So this is going to get us the minimum number, the smaller number. All right. Let's call s the smaller of n and m and l the bigger. All right. So the bigger one is l. So it's going to be define l max of n and m. All right, so that gives us those two numbers. All right, if s is 0, the GCD is just L. All right, so if s, we have this s variable now. So if s is 0, so equal s0, then what? If s is 0, the GCD is just L. All right, so it's just this L over here. Otherwise, the GCD is just GCD s and then L modulo s. All right, otherwise it's just gcd-euclid. So we're going to do a recursive call. That's what it tells us. Otherwise, the GCD is just GCD, the call to GCD, s, and then L modulo s. All right, so s, and then L mod s. So I think it's percentage. It's not percentage, it's mod. Modulo, there we go. All right, so L and s. L and S. All right, there we go. Run this code and all three tests do pass. All right. So no one's expecting you to come up with this algorithm because, you know, usually this takes a mathematician. This is domain knowledge that comes from a mathematician doing research and then transcribing this into a set of operations that you can follow. All right. No one's expecting you to do that, but you should get used to being able to translate this into this code form. All right. And we need to double check, since this is a generative recursion problem, that this actually gets smaller, right? One of these actually gets smaller, and there is a base case. This is the base case where it's 0. And let's see, we're passing this in. So s, like so, if s is equal to 0, so this m, all right, so it's going to take the min, so it's fine. We are getting smaller because it's recursing over the min of n and m. And this is going to get smaller every time. All right, these two. And you can use the stepper to verify that, but nonetheless, all the tests do pass. All right. So now let's move on to problem B. Compare and contrast gcd-structural versus gcd-euclid on big numbers, right? So let's actually review gcd-structural. Produces the greatest common divisor using structural recursion, all right? So it takes the min of the two numbers n and m. Why does it take the minimum? Well, if we're given two numbers, right, like 18 and 24, or 50 and 100, right? We take the minimum because 100 can't go into 50, but 50 can go into 100, right? It is divisible by 100, right? 100 is divisible by 50, all right? So we take the minimum of those, all right? And then we pass it to a helper function. And this helper function is going to do the structural recursion that subtracts 1 until it hits the base case here, where the common divisor is 1. And it does so by checking at each step if they divide by, and they have a remainder of 0, like so. All right, and the problem with the structural recursion approach is that it works, but it's slow. That's why we have to do generative recursion at points where we have smarter and clever algorithms. All right, so let's actually time this. All right, they give us some examples here. So if we run gcd-euclid, let's actually do gcd-structural first. All right, so this is gcd-structural. Takes a while. All right, there we go. It took like 3.8 seconds. All right, compared to the Euclidean version, which is a more clever algorithm that was discovered by mathematicians and that we had to transcribe into code form. If we run this against this, right, how much faster? It takes virtually no time. All right. And that is why we do generative recursion. Some problems can be always solved by structural recursion. Sometimes there are actually some problems that can't be solved by structural recursion. There are some that are, but even if they are, there are generally some faster and more clever ones that you can do in terms of generative recursion. All right. Anywho, that is about it for this video. I recommend that you submit it to Handed, check your score, and I will catch you in the next one.